Hello, my name is Desmond Stevens, and I'm an Associate Professor of Mathematics at Florida A&M University. And in this video, I'm going to talk to you about the relationships between derivatives and concavity. First, let's consider the definition of concave up. So we say a function is concave up if it can hold water. You look at that picture on the right, and you see it looks like a bowl, and it could certainly hold water. Mathematically, a function is concave up at all the c values for which f double prime of c is greater than 0. So wherever the second derivative is greater than 0 on those regions, we say that the function is concave up. Similarly, a function is concave down if it can't hold water. Right, that's an intuitive definition. So you think about a bowl that's upside down and all the water is coming out. Mathematically, it means that the function is concave down at all the c values in a region for which f double prime of c is less than 0. Now let's look at some points where functions might change from concave up or concave down. And so we say an inflection point is where the function changes concavity. Namely, it is changing from concave up to concave down. And these are values x equals c in the domain of the function where the second derivative is equal to 0 or undefined, and there's a change in concavity. So look at the graph on the right. We see in this region the function is concave up, and here the function is concave down. Right in the middle there's a point where the function actually changed from being concave up to concave down, and that would be an inflection point. Similarly, we look on the far right, and there's an area where the function is concave up. Compare that to the region in the middle where the function is concave down, and we see there's a point right in there where that function is changing concavity. So these 2 points are exactly what we call inflection points. Now we can use our second derivative to classify critical values, and that's called the second derivative test. So the second derivative test uses the second derivative to classify critical values, and this means that we're trying to determine if at these critical values is at a location where we have a local maximum or a local minimum. And so the way the test works is that if we let x equals c be a critical value, then if we plug c into the second derivative and that's greater than 0, notice that that would be a place where the function would be concave up, and the red dot would be a local minimum at that critical value c. So where the second derivative is greater than 0 for a critical value there, then we know that we have a local minimum at that x equals c. Similarly, if we took the second derivative on a region and we knew that the second derivative was less than 0, that would indicate that the function was concave down. So if the second derivative at c is less than 0, we're on a region where the function is concave down, and that means we have a local maximum at x equals c. For the circumstance for which we plug the critical value c into the second derivative and it's equal to 0, there's no conclusion. This test is inconclusive, and we'd have to use another test, something like our first derivative test, to determine whether or not we had a local maximum or local minimum at that critical value. So our big takeaways are that the second derivative can be used to determine the concavity of a function, help us find inflection points, and finally, using the second derivative in what we call the second derivative test, it can be used to classify critical values.